It's really exciting. I think this area of explainable AI, right? Like sometimes it feels like there's a lot of buzz, but also I think there is we are starting to see more and more adoption, right? Like
Yeah.
variety of different industries.
And the challenge lies there because it's at that point when the adoption is more, I think it's becomes less explainable AI, but it's actually what AI is doing to your business. Explain to me why I'm getting these business results differently. I don't care what is your AI doing or AI data doing or whatever, but explain to me, right? That becomes the challenge. So it's all becomes multi-layered.
Hi everyone, welcome to today's webinar. We will be recording the webinar and it should be available afterwards. Please share your thoughts and ask questions in the Q&A tab. We'll answer them throughout this webinar. So let me start with just a brief intro about myself. My name is Krishnaram Kintapadi. I'm the Chief AI Officer and Chief Scientist at Fiddler AI. Fiddler, as you perhaps know, is an enterprise startup building a responsible AI and model performance management platform. I have been at Fiddler for about a year, and before that, I led responsible AI-related initiatives at Amazon's AWS machine learning team, as well as LinkedIn AI team. Today, it's my great pleasure to have the Tirtha Jyotish Sarkar or Tirtha as our guest today. Tirtha, would you like to go ahead and introduce yourself?
Sure. My name is Tirtha Jyoti Sarkar. I currently work as a Senior Director of AI ML platform at Rhombus Power, where we solve national security problems using AI, ML, and other data math techniques. Before that, I was with a startup called Adaptix, which dealt with applying AI ML for manufacturing problems and basically machine sensors, data analysis, and anomaly detection, etc. Even before that, for a long time, I was in semiconductor industry in Bay Area, developing actual hardwares and semiconductors for different applications. And there actually started understanding the importance of applying data science and AI problems to, AI techniques and methods to say manufacturing, design, optimization of the large scale product development, hardware product development at that point, not necessarily software. But and there are a lot of this kind of questions also popped up, that basically, why should I trust your new techniques to develop my product or design my product when something is working already? So the trust issues, the explainability issues, the interpretability issues kind of always have been with me. Although I've not majorly formally used a lot of tools, but I have developed my own ideas and tools, and I have seen how to make your AI and ML, if you're introducing something new kind of process to your workflow, then how to design it ground up so that it always remains it's somewhat explainable and interpretable, so that you can always have trust in it. So that's been my focus for a long time.
Thanks, Tirtha. So today we hear a lot about explainable AI, right, or XAI. Maybe can you touch upon why is XAI important for companies?
Yes.
Why is there, are we seeing a growing need for adoption? Like, why is this important?
Yeah, there are two angles to it. One is, and we can share, I think, well, this is actually explainable AI problem or challenge, but we can have a look at the top one, that, but it's actually a challenge of explainable AI. It's not necessarily why companies have to kind of start adopting it, but it's still related to the bigger goal of the purpose, the expanding the scope of the problem and the effectiveness of their business problem that they are trying to solve using AI, just say, so that this still apply. But the main two angles that I see are for a long time, AI ML techniques and tools have been just for a lot of problems, like when the first big data revolution came, then it was just using the data somehow and give some decisions, some classification and stuff like that. So those are the kind of things that earlier was not done. So then it was a new thing, and then people were happy to get just the results, like a personalized recommendation or what have you, whatever Amazon, Facebook all started. But then now more and more we are in many of the companies that I work for, I have seen that we are now trying to solve an established problem which is very well known, and there is actually a solution for it, but now we are replacing the existing solution by AI ML tool, because we know two things. One is that it can learn over time, it can get better, and it can learn from the data, which was not possible from the traditional rule-based or logic-based system. So we are actually replacing the business logic, the rules which have been written for years and years by engineers and practitioners for a long time using AI. Now that is the problem. So now whenever you start replacing something which actually works, has been working for a long time, but now you are starting to replace by something which not a lot of people understand, then you need to explain to them two things. One is basically first how the model is working, but even before that, how explain to them that basically, or have trust, grow trust in them that basically this will actually work. This will first replicate and reproduce the exact results that they are used to see, and then it will make it better. So all these promises that you are making with AI ML, you have to build trust in those promises and give assurance. So basically, and people will generate curiosity. So now once you explain to them that basically it can learn from data, then people will start have this curious question. So I have this site data, I have that data which I was not using, can it learn from that? And then they will ask, okay, show me a proof where I can understand, the interpret, the how it is ERP. So all these side questions popping up in people's head when you are introducing a new tool, a new flow, like with AI ML, because they are saying that, oh, we already do it, so why do it? First, convince me, and second, basically, build my trust. So because of this, deep-rooted engineering and verification and validation mentality that engineers generally have, this need for explainability and interpretability is growing, so fast. That's actually, I guess, the main impetus behind it, drive behind it.
Yeah, that's a great Tirtha. Like it's kind of as you were mentioning, right? There is now, with the wider adoption of the AI or machine learning models, we're starting to see more and more need for explainability. So if we can add a few related thoughts.
Yes.
I'm kind of, we are seeing broadly at least from three different angles, right? There is an interest in explainability. So one angle is from a business perspective, right? If there is a machine learning model being deployed for a critical system, let's say system that decides how to schedule different trains, right? If something goes wrong, then maybe there may be a collision, or how to kind of decide, or where to set
administer a drug or a healthcare profession,
right? Right. So where to say, let's say, set up the next set of solar panels, right? Or where we are likely to get minerals or oil and so on. Like there is a large amount of stake involved. So there is just from a purely business angle, right? Instead of treating the AI model as opaque, there is an interest in understanding how the model is making decisions. Is that aligned with the domain knowledge or domain intuition? Right? That's one kind of broad interest we are seeing. And
I would add to that one thing, Krishna, is that this is also a very interesting conversation I had with somebody. And basically, I was thinking one time is that, those domains earlier, let's say a mineral discovery or oil discovery or drug discovery or something like that. Earlier, we used to say, well, that's actually a domain of experts. Very, very few experts in the world understand this. You will not understand that. So don't ask for even how we discovered the drug kind of thing. On the one hand, actually, there is a message on social media, on everywhere, for young people, data scientists, and all stakeholders also, that AI is actually democratizing. It's actually democracy. It will bring data democracy. It will bring data literacy, etc. That means it's very little entry of barrier in. I mean, if you want to learn it, sky is the limit. So you can also understand it. Now the thing is that people are saying, okay, here, so you cannot have both ways, right? earlier you were saying that you were using very sophisticated scientific tools, which I have no training for, and that's how you discover something. Now you're saying just you discover from data patterns. I can do some data patterns. I have learned some. So you need to tell me if you're using the similar kind of AI models that I have heard about, I have got trained on. Then you need to build trust in me in this process, or you need to interpret that basically using those things that I know a little bit, how you got these results, right? So the familiarity of the techniques and tools that we say, let's say you make a decision on financial or healthcare or something, and then actually somebody comes and probes you that exactly what did you use? I use some neural network or some support vector machine. Oh, I have heard them. I have learned about them. It's not something esoteric scientific concept you're talking about. You were telling the names of the models and techniques that they have heard about. Now they will probe deeper. Their curiosity grows. Then, okay, using this, which I know, can you explain to me? This is natural questions, right? Because they're in the familiar zone now. This is actually happening. I have seen that. Because
yes,
democratization.
I think like with this kind of growing interest for end users, right? There's often this need for providing the explanations to end users, right? Like, let's say suppose a doctor or a domain expert is using some machine learning model as part of the decision making. It becomes important if the end user, right, in this case the patient, wants to know why I'm being diagnosed with this condition or why I'm being prescribed this medication, there is a need to explain, right? I think that becomes important, and even for the doctor to build trust in this AI model, they need to understand how the model is working. Is that
because it is going from the abstract human thought. Now you're saying that, oh, earlier a doctor diagnosed, now you're saying data actually diagnosed you, like that way. Then you say, okay, data diagnosis, then it's a mathematical process, right? Any rational person will rationalize like that. Then you should be able to explain to me. It's not I'm to explain you your doctor's brain chemistry. It's some data model, right? It's a math. Explain to me, try your best, and let's see if I understand or not. It's a natural demand. So that
it's kind of specifically, right? This is like we kind of spoke about from the need from the business user, or even the kind of the doctor or any domain expert using the AI. Even from the perspective of the model developer themselves, like often we see a need, right? Like they may want to often debug predictions or mispredictions. If the more invariably any AI or machine learning system or model will make a few mistakes, it won't be 100% accurate. When those mistakes are made, the model developer may, or even some customer support representative may want to understand why the model is making those mistakes. What is responsible, which features perhaps caused the model to make that prediction. And then when they discover that maybe some niche feature was responsible for the prediction, and it could turn out that that feature's value was perhaps incorrect, right? Maybe there was some bug somewhere or some data corruption, and suddenly like this value that you expect to be in some 5 to 10 range, suddenly like now it is 100 or negative to 100 and so on, right?
Yes. So this is the second visual aid that I was trying to show on that one, in that basically the modeler, let's say engineer, sometimes he or she wants to explain the model results himself or herself, and then there are two types of data that human beings can deal with. One is kind of tabular data, which is not easy for human beings to make sense actually, because if you're given a table of numbers, it's not, but you can actually build explainable simple model for it. But if you have some other kind of data, which our brain has been, evolution has taught us, like image or audio or something, or natural language, then it's hard to build an explainable model, but actually human beings fare much better. So this is always this tug of war challenge, where basically I do not understand the prediction of my model when I'm building this, but where exactly I need to put my effort to make it explainable, which type of models I should choose. So that's what exactly we are talking about there. This is a dual kind of game.
Right, exactly, right? Like I think this is and talking of interpretability, like can you maybe touch upon so what is the difference, right? Difference between what do we mean by interpretability and what do we mean by explainability? Is there a difference?
Yeah, so I think I have seen, to my best of my knowledge, the interpretability is little more mechanic centric, in the sense that basically, let's say you have a machine learning flow. And then you want to have, you can actually say, I can attach the interpretability. And always I want to measure some degree of interpretability with particular components of this flow, which components means different models. So because any machine learning system has comprised of multiple models, they're interacting with each other, etc. It's not a one thing. So you can probe some questions, or you can probe some data driven or some kind of tools, and then you get back an interpretability score. So that kind of interpretability. But explainability, I guess it is more, it's higher order. The whole AI philosophy, in the sense, or AI adoption process, that you are replacing an existing business process, or you are empowering it more, or you are enhancing it, augmenting it. Now you have to explain why AI should be used, how it is better. All these things of other business explainability also kind of gets blended in with the AI explainability when you bring AI to the as a hammer to solve your problem. So that's actually, it's a little bit higher order in my definition. And the interpretability you can assign to models, process, data, distributions, whatever you are probing, you can have more good measure of. So you can compare with something. Yeah.
Maybe if I think of a specific example, right? Let's take say models like DeepMind's AlphaZero, right, or AlphaFold, doing, or similar models doing better than humans at playing chess or Go, or in this case, right, like discovering new drugs. So this model itself may not be interpretable, right? It's like perhaps a deep neural network with a large number of parameters, and that even the model developer themselves may not be able to understand. But once we notice that this model is doing better than humans, right, or playing kind of superhuman moves, then there is a desire to go and understand how the model is making that decision, right? Like the humans are now, the chess experts are starting to understand these models like this, right? Or Go experts are understanding how these models are making decisions. Is there something like, it's almost like treating the model almost like an natural science, right? Some kind of observation, and now we are trying to understand how this model is behaving, just like we want to understand how our human cells behave, or how right, the planets behave. Like similarly, we are trying to understand almost from a natural science like angle.
Right. And this is the way science developed. Like, okay, there was data first collected by, if you think about, I mean, I actually show this slide. It's my one of the favorite, because I say that data science actually existed in 15th century or 16th century also, because that's how the science started. Before science, there was data science. In the sense, Copernicus and Tycho Brahe, actually, they did the observations, and Kepler formed empirical laws about the planetary motions. This is how he did. He just fitted the data. He saw the motions of the planet, and then the cube square law, etc. Then Newton came, and that was the data feeding part. Okay, now, so that was like a model. You put in a planet's rotation motion, you can get some answers, some prediction, but it was not explained why. Why is the gravity? What is the actual mechanism? So now the Newton came and kind of gave rise to actual underlying thing, that basically whatever apple falls, the same force acts at a universal scale. So that was the understanding. That's the science part of it. So first come the observation, then come the data modeling or data fitting, and then you have to understand how the results are generated, or how actually the mechanics of the nature works, or in this case, an artifact of the nature, which is our artificial neural network, which is kind of trying to mimic a biological entity, how it is working. And also, Krishna, the challenges and limitation, because it's as you said earlier, that these are now, playing Go and chess is great, but then now when you're moving into drug and protein folding predictions and new kind of thing, the stakes are so high that the models can be fragile in their own ways, and unless you understand them, the kind of their overall mechanism or mechanics, then basically you will not be able to understand the challenges and limitations. Because even I remember in AlphaGo, even the Netflix documentary, it is shown that, one time the one match Lee Sedol won against the AlphaGo, he made an total unusual, unexpected move, and that was not in the calculation decision tree, not decision tree, the Monte Carlo search tree of the AlphaGo, right? So in that case, it did not find a solution. So basically, it was defeated, right? So that was kind of weak spot, and it of course with playing more, it got better. But then understanding those weak spots is very important when the model or those kind of same systems are applied to much high stakes prediction game, I would call that's the kind of drive should be goal and drive for all these companies which are developing these models. And
I think that's a great point. Like, often, right, these machine learning models are not used in isolation. Like, if you think of like this doctor example, right, there may be a machine learning model which a doctor or a radiologist may be using, or let's say in the case of financial services, a lender may be using, but they are combining their domain expertise. Yes. Or human agency along with machine learning model. So it's all the more important to understand what are the limitations of the model, so that when you are getting to those regions, yes, you can rely less on the model and instead defer to the human expert, right? Like who can override or make the decision.
Right. I mean, it's not only purely human human expert is a layer, but I can give you a very concrete and a simple example from my previous startup that I used to work. So there we used to use machine learning model to catch anomalies and actually in a machine, like a manufacturing machines in a flow, right? And then we provide control actions, means how we should move the machines. Now, this is dangerous because if you completely rely on the machine learning model and you do not understand the interpretation or the mechanics, then it can suggest you the control actions which can make the machines like move really fast or like become dangerous for the operators. So you need to put actually control logic on top of the machine learning recommendation. So it's not human beings will not be in the loop, but still you put some rules-based checks and balances on top of the machine learning results, right? And then if you understand the limitation, then you can put the checks and balances. So even if it's totally software driven, even if it's not even human being even looking at it, still you need to make those software which sits on top of the decision layer of the machine learning based upon the understanding of the machine learning model deeply. Otherwise, you will not make a reliable system which you can ship to customers, or a safe and reliable system which you can put in your factory floor. That's what we saw. I mean, we always put those layers, right? And if you put the layers without understanding the machine learning model, then it will be less effective layers, less optimized layer. So that's the goal. To make
yes, I think that's yes. When it comes to those kind of applications, let's say robots moving in warehouse, safety becomes so important. Like, or if there is a machine learning model which is detecting humans who are walking, and uses that information to make sure that the robots or the automated robots are not going and hitting them. Now we need to understand, okay, is this model working well for perhaps people of all skin tones or all genders or all age groups? If there is some segment where the model is not going to work well, that has a huge safety and other implications, right? Regulatory implications. I think that becomes like understanding this robustness or limitations, or like how robust is the model becomes really important. So along the going back to this interpretability discussion, right? You started mentioning about human performance and interpretability. Like, could you maybe touch more upon that?
So
you also had a slide on that.
Yeah, I mean, in the sense that they act, in a sense that if we want to measure the interpretability of the model, actually an easier method is to have a human being perform the same work, and you say, oh, I can predict exactly what the model will also predict before the model predicts, because I'm not seeing, it's a blind kind of experiment, right? And if a human can kind of replicate the thing, then I understand, oh yeah, human beings can understand the model behavior, but because this guy can predict exactly what the model is going to predict. So it's like a match-up game, and I kind of match up score. So it's easy, but it is dangerous in some cases. So basically, I in one of my article, I kind of trying to argue that we should avoid this kind of measure of interpretability, consistently predict, because human beings. So let's say next slide, if I go to on that thing that I have, see, there is two types of data sets we can talk about, and we and by image data I don't mean not necessarily image, but it's audio, video, image, high dimensional data, natural language processing, which is big in machine learning model. So it's a continuous struggle between this thing, human performance and interpretability. Actually, they go like little bit, it's a tug of war on different type of data sets. If you're given a big table, as I was saying, they're basically numbers, right? And then you have a simple classification. Let's say a famous like data scientist, young data scientist, when they start with, they all do this. So IRIS data sets, they practice on the or wine quality determination classification problem. Very common. I teach them in the machine learning courses. They have a bunch of numbers, some chemical analysis, and ultimately you are building a logistic regression model to predict the quality of classification, yes or no, or good and bad, good, bad, ugly. Now, just by looking at the raw numbers, the features, human beings will perform very poorly because our brain is not developed to, evolution has not made us, superior to deal with a lot of numbers. Numbers crunching only started 8,000 years. Human brain cognition revolution started 70,000 years ago. But we are very good with looking at something and understanding it, right? Because that's how the image problem, understanding the natural language, the nuances of the tones and how people talk to us. Those are difficult for machines, and that's why you need to build very highly parameterized billion parameter BERT and GPT and all those big models for them. So then interpretability goes down on those models. Humans will perform better, but the interpretability. So then now you try to compare human performance with interpretability, you'll get a conflict. So my point is that you should not use human performance as a interpretability measure. You should have model agnostic, like an independent mathematical tool, like more visualization tools. You need to research more and come up with independently of how human being is doing a particular model or data set. You should be able to try to attack that model, peel up the layers and kind of get the interpretability scores independently of just a human performance, because human performance is not reliable on various types. It's so much variance will be there, and that's one of the premise of going to AI anyway. You want to make the variance low across the task, across the kind of thing, and so you need to apply the same philosophy in terms of the interpretability metric that you want to measure or score you want to develop for your performance.
I think that's a great insight. Like if you look at this area around evaluating explainability techniques,
right.
One measure often used is known as fidelity. It's around what happens. So let's say that there is an explainability method, and it suggests that a specific feature is responsible for, or most responsible for, the prediction, right? Or it ranks the features in terms of their importances. So the intuition of this approach is now you start removing these features one by one, right? The most important features. And you look at what point the model's prediction changes. And that is like, if there are two explanation methods, and turns out that for the first explanation method, you have to remove maybe 75% of the attribution before the model prediction changes. Whereas for the second one, once you remove, say, even 20% of the model at the feature attribution, the prediction changes, then the second method is better because it's able to capture the most important features correctly, right? Like there are ways to do these kinds of evaluations without necessarily bringing in the kind of subjectivity
right.
of humans, right? When it comes to whether they find the explanations useful or not. And there are, of course, also studies on what happens when you combine, when you just present the results from the machine learning model, when you combine those with the explanations provided by the explainability technique, and so forth, right? Like what happens, how does the behavior change? And sometimes it's not just there is some element of even psychology or human behavioral aspect to this, right? It's not purely like whether it's from the machine learning model or machine learning model and explanations. Often we as humans tend to trust machine learning models a lot more than we may really need to, right? Like there are all those aspects. So maybe I'll just pivot and go into some of the questions that are coming up, right? Like so one comment or question I see is, apart from elaborating on these kind of definitions and the need for explainable AI, are we going to go into detailed discussion of the functionality that Fiddler offers around explaining models? I would say perhaps not, because this webinar is meant to be more broader, and from the angle of Red, it's more from an educational angle. If you are interested in the Fiddler specific aspects, please, we'd be more than happy to set up some time and walk you through those. And in fact, after the webinar, you'd be receiving like a summary of the link to this today's video, and along with a few additional pointers from our team. So let me go to another question, which is, can explainable AI help identify which features we should focus on during model development, training, and production?
Yeah, of course. I mean, that is the central goal actually of many of the tools and techniques. And that's part of the ground up design of the model, thinking about how you, when you write a code for a kind of system or something like that, what kind of metrics you are developing. And also you have to understand the business, I guess, the ultimate curiosity that human beings, you have to anticipate. So that's where the psychology things also a little bit come up. So you know you are developing some model or ML system for some answering some question, or some solving some business problem. You have to little bit anticipate that what kind of explainability, what level of explainability question will come at the end, and that's how you will start, collecting those data so that you can explain it. For example, I think it will not answer it fully, this question, but there are some. This is actually related to a manufacturing problem, but I need to explain this graphic a little bit. Is that it's a very simple. So basically, you can actually start collecting. For example, people say, oh, if you show a bunch of correlation, maybe that will explain why your feature was strongly correlated with the results, and then you can explain it better, right? That's the one type of explainability. So I will always calculate the correlation score. I will keep it in the in a store, and basically I will just do a nice visualization, a lot of scatter plots, and I'll show, oh, some of the plots are have some pattern, etc. Because that's how traditionally we have been doing, and so you're ready for it. But then it becomes cognitively, actually I have seen, too much overwhelming sometimes, of course, because when the features start exploding and becomes high dimensional data, you have hundreds of features. So how many plots you will build? You cannot make the overall, your goal is to make the overall your system trustable and trustworthy and explainable, right? And you will fail at that if you are with there's many features you're trying to do the same old thing. Instead, maybe it's actually useful to focus on, anticipate and focus on the higher level question that you will get, in the sense that they're interested for this particular problem, they're interested in correlation, but ultimately correlation leading to anti-correlation or outliers in performance. Basically 10 machines are operating in a manufacturing floor, and a couple of them they know, but they do not know exactly which one of them are actually falling behind the others, and etc. So and you can do a lot of time series data, and you can do time series correlation, etc. You can build those charts. But instead of that, if you build a very simple visualization kind of chart where you calculate particularly what exactly they're interested in at the business level, and then you show my machine can explain to you why the difference. That's it. I'm not trying to explain you the raw data, the pattern, the time series, nothing. Not all the modeling stuff, the detailed modeling stuff I'm doing. I'm not explaining how my model works. I'm explaining to you only how my model is detecting the difference between your standard operation and your expected operation that you are getting. So that much part. And it may not be fully modeled. Maybe the model is giving you some numbers, which comes like 70% of that process, and then 30% you are doing some simple business logic calculation with those numbers, output of the model, and that 100%, that total calculation is giving you the measure of the difference between your expected performance and your actual performance. And that's all they're interested in, the 30% difference or the expected performance difference. That's all the stakeholders are interested in. So you build in your code or in your ML system the whole thing which you anticipated that this question you'll get, and you build this score metric so that you can visualize it quickly and you can make it so that this method actually, in my experience, have been much easier to may not be easier to deploy, but I mean, you have to still plan for it, but once you do it, then it becomes easier for convince the stakeholders. So anticipating the curiosity of what kind of explainability question you will get, and planning for it is so much important.
So it's kind of since you talked about correlation, right?
Yes.
Another question we have is how do explainability methods distinguish between correlation and causation?
Well, I mean, it probably does not, even the famous Shapley values, it's actually about the marginal contribution. I mean, by definition, if you think about the Shapley values and all those things, it's still it was developed in economic model perspective, and then it's attribution kind of techniques, and mostly the explainability techniques that we use as tools, that I can tell you if you remove this feature, or if I make a combination, or if I have this feature and do not have this feature, then what is the difference in your performance. So you see a difference, and if you believe that basically there is a causal process in it between having it or not having it, then you probably can say that this feature is important because I'm seeing a marked difference. But it actually cannot guarantee that basically there is a causation. But I will tell you this thing also. This is kind of sometimes sound to me myself a little bit kind of it's weird, because if you are not talking about, let's say I do not tell you that machine learning is happening or anything fancy things are happening. I just show you that I considered this factor, I did not consider this factor, and see the difference in the outcome. If I just tell you at that level, psychologically, I can guarantee you that a lot of human will say, I mean, the stakeholders or whoever your audience will say, oh, so you did not consider this factor in this business process or your calculation, and now you considered, and I'm seeing some difference. Maybe this is causing it, right? Because this is natural way we interpret things. So if you hide the abstraction of the calculations of Shapley values, but just float up the essential nature of the kind of calculation, that basically if I take it out, this feature, and then introduce it, and then I took out this other feature and then introduced it, and this is the difference. There is a large difference. I am not even saying marginal contribution and all the calculation, all the nitty-gritty, but I'm saying that it's a good difference, large difference, recognizable difference. Then I think if you talk at that level, then who wants to hear that basically there is some kind of causation, that kind of person you can satisfy, at least from a conversational point of view. If your goal is to satisfy the stakeholders who wants to hear that basically that at that level, then basically you will be successful. But you have to package your presentation. You're doing the same methods and metrics, but you are removing you're doing more abstraction, removing the kind of exact calculations or nitty-gritty details from it and presenting in that way.
Yes, I think that's a great segue into causation and correlation, right? And in fact, even from a research or academic literature, there is a lot of work on relationships between causality, right? Causal models and explainability, and whether we can automatically learn causal models from the existing data sets, or if we have domain knowledge and we are able to provide causal relationships, can that be leveraged as part of the explanation computation? And there is a lot of, I would say, debate in this community on can explainability techniques work without necessarily needing this kind of causal information, and also like this aspect of, is it even possible in most real world conditions to provide neat causal relationships, right? Like often we hear examples such as if it rains, it gets wet, right? There is a causal relationship, but can we provide similar causal relationships when it comes to maybe like a real world setting, right? Whether it's lending or hiring, healthcare, manufacturing, and so forth. So kind of maybe going into a slightly different direction, like in your past roles, right? Have you applied explainable AI in various machine learning models? Can you maybe go into some of the like practical experiences, right? What are the insights you have learned in the process of building machine learning models, and specifically like when it comes to applying explainability techniques?
Yeah, I think some of the things that insights I mostly I can talk about some of those manufacturing problems where I had to apply or always try to keep. So some of the explainability metrics ready because I knew that this question will come out. One of the reasons was that, as I was telling in the beginning, many of the situations that I have faced in my career is that where I am not introducing a completely new way of data crunching and AI leading to that, but it's an existing process, not necessarily a software process, but as a product development, a hardware, or kind of material science or something like that, where you are using, now you're introducing AI and machine learning for making it better, or design process, making it faster and more efficient and less error prone, more optimized, etc. Right? So it's more of the same, and then you have to defend the AI and ML techniques with because people will be asked, why should I trust it, right? That's the fundamental question. So in those cases, it becomes more difficult because you first of all, to get into the inside the door, you have to have not only the performance metrics ready, but also some of the trust metrics ready for the machine learning. So that's the first thing. So you need to anticipate what kind of problems you're solving with AI. Is it brand new problem which you are not solved before? You will have actually less resistance or friction in terms of explainability if you are solving, because first people want the solution. In those cases, they could not done it without the AI. But if you had an existing process which you're improving using AI, you will have much more explainability questions and resistance and friction, because then people will say, oh, I know it already works, you are improving it, and I understand somehow using the data, but now I need to understand the trust, right? That's the first thing I will start. So that's a big insight. Then you have to separate out. You may, in your application, you will have both kinds of problems that you're applying the AI for, and so basically you need to have prepare for the second one much harder. And then actually the main thing that I learned again, which I touched upon in the previous discussion, is that you always, in the explainability tool choice and matrix choice, you need to anticipate in time that basically what kind of curiosity, what kind of scope creep that they will have, because first it will start like that. If I can go back to this one, the first one is that the human curiosity is unbounded. So whenever you go into this explainability and trust, this kind of problem or questions, then people will have, okay, what's the purpose of explanation? What's the scope, and how effective is the explanation? All this question will come, right? So, and this actually starts with a nice definition. You'll probably think in your mind that I have this model and I will explain the feature importance of this model, and that will be good enough, right? So that's your scope definition and your purpose, and it can explain certain things. That's the effectiveness of your model process, explainability matrix that you choose. But then scope creep will happen. So the purpose will be completely different. You are not explaining that model's performance. Maybe you are explaining a couple of models interactions explainability. You did not plan for that, right? So that's the kind of anticipation you have to make. And then also all the kinds of new questions will come. People will move from models, exact model output performance explanation, to how this model is leading to downstream business process decision making change. They will ask you all these questions, right? So that's kind of practical situation I have seen happening. So you need to prepare for what kind of things questions you will get, and then always the good way to prepare for is the counterfactual. That means you always have a ready. Counterfactuals also goes like a fundamental feature change and then Shapley value. This actually built upon the counterfactual. What if I don't have this, right? Now instead of just thinking in terms of Shapley values or narrow kind of techniques, these counterfactuals are about whether I have this AI, these three models in this sequence, with these parameters in your process, or I do not. I take out the whole model. I'm not taking out now the feature. I'm taking out the whole model. I'm introducing the model with a different model, different genre of model, etc. And then I'm showing all the experimental result to you, how things are changing, your ultimate business decisions are changing. And at that level, when you talk about those business decisions level, then people will understand that, oh, big changes are happening, because for them that is the they can recognize those changes. Because if you show accuracy metrics of a classification model or regression score changing a little bit, and you calculate the sensitivity with this feature importance, for a lot of stakeholders, at high level stakeholders, it will not matter much. But basically, if you show the large business decision changing, by taking out the whole model. So because you're thinking the question will come, what if I don't have this AI model? What if I don't have it developed in right time, etc.? Then what happened? How the process outcome looks like, right? So that will be the kind of question I have got in my career, and that's kind of, I think, is very common in many practical scenarios. So the
Yes, I think
heuristic
this idea of counterfactuals is very closely related to
yes.
the value provided by the machine learning model,
Yeah.
or even specifically like some of the inputs, feature inputs, right? In fact, interestingly, like the name Fiddler comes from the ability to fiddle or perform counterfactuals, right? In fact, one of the core functionality we offer is given the ability to change, modify the inputs, feature values, and see what's the effect on the model's prediction, as well as what's the effect on the relative importances of different features, so that you can kind of know if the income increases, what is the likelihood of churn, or if the likelihood of the being reliable to be offered a loan, how does that change, and is it aligned with our human expectation or the domain knowledge as well.
And related to that, Krishna, is the synthetic data generation. Also, I found very useful techniques for a lot of those, because ultimately you want to change the distribution level, kind of data. And in many cases, you will not have the actual data to sample from. So basically, in many of the system, I built a parallel system, which is kind of mimicking the process, the data flow and everything, where I manipulate the incoming data, but I can manipulate very controllably. There, I can choose the distribution, I can shift them, etc. So building this synthetic data generation engine, which mimics your existing process flow data, real world data. So you have to use probably very sophisticated machine learning generative models or something to begin with, to first mimic them, and then you have full control. Then you can perform those counterfactual examples much more, with much more confidence to show. Otherwise, you have to depend upon the existing data. You say, I sampled from this particular days of data, and see your performance is different, other days different. Then people will say, oh no, other day it was coming from different supplier or vendor, so reason is completely different. You don't know. But you don't have control over that, experiment. When you're doing experiment as a scientist, you should have like good control over the variables. So synthetic data for data distribution changes, because you're probing like Krishna said, like your counterfactuals means you're probing the features, their changes in their sequence, their appearance, whether they are there or not, and their distribution, right? All of these aspects. Basically, you should have control over all of these aspects.
Yes, I think that's a great point. That kind of partly addresses one of the other questions we got, which is that if you observe, say, correlation between this famous example of the number of birds in a country and the number of storks in a country, you might see some correlation. Right? That doesn't mean that there is any causation or relationship between these two. So kind of observing and measuring correlation itself is not adequate, and that's where I think the ability to perform counterfactuals, or the way in which explainability techniques like Shapley value based techniques use some form of counterfactuals, right? Like changing the features, it helps break and at least to a good extent differentiate between just pure correlation and causation. So there is, since you have been talking about interpretability and explainability, like sometimes we hear this discussion that explainability itself is not needed, right? Instead, isn't it better or enough for the models to be interpretable? Like, do you have thoughts on this?
No, I actually do not subscribe, because it is probably works for if you have model interpretability, like you build simple models and everything. Like say you have a choice between, you should make that choice if you know that you have to interpret your model's result. Then probably you should not build too much black box big parameter model unless you have to. Right? You should not, apply the same neural network for everything problem. You should start with the simplest model that you can interpret the results reliably. So you should have that mindset when you are designing a system as an engineer, but you cannot rely on that. If you are thinking that way, that then basically you are limiting yourself to making the interpretation or explanation only up to a certain level of other engineers on the other side, like client engineers who wants to understand. You go to a little bit higher stakeholders, they will give you example. They say that, I mean, as I told you again and again, this may be very new, I mean, particular to my experience, my life experience and my professional experience, is that more, this is actually becoming more true. The machine learning and AI was novel 20 years back or 10 years back. Now it is being applied to problems where solutions exist. The world is not static. I mean, we have sent men to moon without machine learning, right? I mean, there was no machine learning that time. So that much engineering feat was done. Not much computing either. In 1960s, come on, think of it, right? So basically the difficult engineering problems have been solved for a long time. And good engineers, I have heard from my bosses and other things that I have solved this problem using my intuition. So basically you have to give me, when you are introducing some things which I do not understand fully, you have to give me some things to hold on to, right? So some explainability. So you have to aim for higher level business process explainability, which can be synthesized or composed by individual model interpretability measures or other way, or by a simple combination of thereof. But you should always aim to try to build some story, at least for the high level explainability.
Yeah.
Otherwise, you fail in your bigger purpose.
Yeah, yes, absolutely. I think it doesn't. I also kind of more or less agree with you that often, right, like for certain classes of data sets or maybe problems, fully interpretable models would be desirable and would work great, right? But when it comes to especially like cognitive related tasks, right, like image or speech,
Yes.
or video and so forth, or broadly like unstructured data or multimodal settings, like we have not seen a lot of cases where the interpretable models are doing at least as good as the deep neural network based models. But at the same time, there is a desire to understand how these deep neural network based models are working, right? In spite of we going with, say, let's say deep neural network based models, whether we can articulate this is what this particular part of the neural network is doing, right? There is a shift towards that.
Yeah. And this is a very simple example, if I can add there, is that for image classifications kind of thing, I mean, everybody kind of familiar with that problem. So you can actually you can do a parallel experiment and can make your model interpret. So for example, you have an image classification problem and you applied a convolutional neural network. Okay, so ultimately, if you know that the convolutional neural network is actually creating filters, the convolutional filters, which actually earlier were used to be rule-based. Now the filters are being learned from the data. Okay, but then at the end, maybe you cannot explain the every working of the every layer of a convolutional neural network. But when it comes to explainability, I have applied this technique myself, is that I said, okay, my CNN will work on my actual data, but I will explain the working of the CNN in a different way. I will take simple filters like edge detectors and stuff like that, and I'll apply a logistic regression on top of it, like classifier. I bring the features, and basically these features are like 5 or 6 features, right? And then I can show that, simple logistic regression classifier, because ultimately that is the thing. If I have a sigmoid activation function at the end of neural network for classification, it is actually a logistic regression on top of nonlinear filters. But I do not need to go into the details of nonlinear filters, which I cannot explain, but I can explain simple image processing filters, and that they are very familiar with, the convention, people who have been using it for the last 20 years. So now they understood, and I just tell them, look, this is the same thing. Nothing is changing. Now you are having continuous improvement of the same thing, but learning by data. You do not have to define those filters. So this is the way you break up the explainability task, the burden on yourself. You explain it in the familiar terms, but you also add the thing that the machine learning will help you learn continuously from this thing and do the things better, right? So basically you explain familiar term, but basically you see that serves your purpose. Ultimately, you want to get your machine learning flow in, right? So this is the kind of techniques I have used also.
So let's say that perhaps many data scientists, right, or ML practitioners by now are convinced of the need for explainability techniques, right? Do you have thoughts on how they can show the value that explainability brings to maybe the business decision makers, right? To the leaders at an organization. Like, do you have thoughts on how can they articulate the why an organization itself should adopt explainable AI approaches?
Yeah, actually, this is a very good question. I was thinking in a little bit downstream way, but your question is general in the sense that there are two kinds of audience an engineer or a data scientist needs to have the. I mean, he or she needs to kind of explain that why explainability is needed. Two kinds of audience. One is actually his or her peer group. That means why, when you are building an ML system, why you should always think of explainability. That he can demonstrate by showing that basically that data scientist goes and presents to a stakeholder, and with it's always, my mentality is like scientist, so I always say this and that, right? You do not have this, so basically what's the difference in the outcome? So it's like outcome based analysis or data driven analysis. So that means one time you present a machine learning experiment or machine learning performance results just in a descriptive manner, that this is the performance, I applied that, this is the accuracy metrics and all this thing. And then in another case, you present with the explainability because you build the model that way, you throw in some additional results, which are not necessarily the performance metrics, but which are showing that basically what features are most important, ranking, and what happens if you take them. So counterfactuals example. Most of the machine learning presentation, you will not find many counterfactual examples. That's extra work. It's not part of the standard process. You have to write extra code to record them, experiment them, perform those combinations and get those results, right? So if you show them and then you actually get a response, you record that, how fast your machine learning idea or your model gets adopted in the main flow in the company or in an organization. That's actually a direct measure of showing the utility of adopting explainability to the peer group. And the same idea can be floated up to the higher level, that basically now the judges are actually from external, of course, the clients and the customers, that basically how easily you can push through your new product with the new features. Why you need to, let's say you are introducing some machine learning features on your software, and that actually needs a slight price change on your contract or some kind of a new product, right? That so how easily you can justify that price increase on your software, enterprise software flow or something, a licensing fee by so they will say, okay, I'm getting this, I'm just dry numbers of I'm getting better prediction. It does not mean anything. So basically but if you're telling me that basically I can now trust more because of these reasons on your prediction, then it is much more, I can understand those languages because I'm the layman, right, who's using your product for and you have put machine learning AI, I don't care whether it's magic or AI, but you increase my trust. So at that level, if you want to show that by having those results and very simple kind of visualizations and simple good enough results, means you change this to that and it went from performance from not acceptable to good enough, not the best one, because you cannot never determine the best optimized value during all kinds of feature permutations, because that's what the exponential problem. But you did some experiments and you found a good enough place. So you that's the kind of explainability you're building, that basically you can explain the good enough results improvement by doing this techniques, whatever explainability techniques you're using. So if you can convince that, then the higher stakeholders, the VPs and the directors, they are also going to start using them more in their external communication. I think that's actually good for the organization to move to. So now you have propagated the idea of this whole explainability throughout the organization, at the engineering level and at the decision-making level also. Customer.
I think that's a great point. Like what I have often seen is when it comes to the benefits of explainability from the perspective of, say, meeting regulatory requirements and so forth, often that it flows top down, because maybe the compliance team or the chief or the data officer or CTO, right, or even sometimes CEOs, they want to adopt explainability and fairness and privacy and related techniques, and then that goes top down. But the one way the practitioners, data scientists, machine learning engineers, right, other ML practitioners can help articulate is by showing that using explainability techniques often reduces the time to detect issues, right? Time to debug mispredictions, and the fact that using these kind of techniques helps design maybe better features, right?
Yes.
Faster
design cycle, faster iteration.
Okay, faster design cycle, because often these things translate to lesser time spent, or it translates to faster pace and for better business metrics.
Yeah,
right?
great example is that operations floor on a machine or a manufacturing. That manager, he's a mechanical engineer or manufacturing background. He doesn't know anything about machine learning. But if you say, if I have explainable features and that pops up, right? I mean, this feature is important, that feature is important. Then your chemical engineers or your process engineers, they are going to look at those features first. That will save you much more on the operations time and the material cost and everything. And that came because I designed my system ground up with those things in mind. So you do not talk about anything about actually machine learning model or anything Shapley values, nothing. You just told him that you save his time and cost of the materials or design cycle by incorporating something. I mean, that's it. I mean, you leave it that and then see how it changes the acceptability.
Yeah, that's a great way to maybe conclude this discussion, right? Like, even for people who may not be familiar with machine learning and AI, it's to convince them, right, to adopt such explainability techniques. It's to demonstrate how that helps in that specific domain, right? I think that's the best way to do this. And I think we are just at the time, and I would like to thank everybody for joining us today. Thanks, Tirtha, for sharing your insights as part of our AI webinar series. And we look forward to seeing all of you in the next series, likely a few weeks from now. Thank you all once again.
Thank you. Very nice to talk to you, Krishna, and thanks for the opportunity to talk later also. Bye.
Bye.